In my last video, I talked about roller coaster safety. Now, how many of those concepts did I bring to my dark ride? Most of them. Let's break down the mechanical design, communication failure detection, and operator controls that make this ride safe. This is my Trackless dark ride. It's driven by a Raspberry Pi and a bunch of microcontrollers. And it uses all these ArUco markers on the floor to tell where it is, and from there it can tell where to go. Now, it's not nearly as dangerous as a roller coaster. It's light, it's relatively slow, and can be stopped just by cutting power. No need to worry about brakes. And the operator is constantly watching the ride go with their finger over the e-stop button, ready to stop the ride at any moment. All that means is that there's already a baseline layer of safety from the design of this ride, so I don't have to be as strict as I would be for a roller coaster. The mechanical design of this ride already has a lot of safety. The rider sits fully within the frame of the vehicle, so even if it does crash, there's no risk of being crushed. You can see here that my feet are within the footrest, and the rest of my body is encapsulated by the armrests. There's no way for me to hit the wall like this. The wheelchair was originally designed to be driven around manually, so those engineers expected it to crash. This is unlike a lot of rides where there's never meant to be any collision. Also, the max speed of this vehicle is slow enough that even the most intense crash won't cause whiplash or anything like that. Plus, because of the suspension system on the vehicle, I'm not worried about tipping or anything like that happening on this ride. This is great because it means I don't need to limit the speed or limit the turn rate through the control system. This adds another layer of safety just through the mechanical design of this vehicle. If you remember my video about roller coaster safety, I talked about safety PLCs and how their two-processor design guarantees that even if one processor fails, the ride will come to a stop safely. So do I have the same system in my ride? Do I have two processors like that? Well, I've got a Raspberry Pi on board. A Raspberry Pi isn't safety rated in any sense of the word. So why am I still comfortable doing this? Whee! It's because of the hardware safety we already talked about, and the actual chances of a processor failing this way are very, very low. But just because a Raspberry Pi isn't safety rated, that doesn't mean I didn't include any safety features into the program. Let's go over all the safety features on this ride. There's a lot of communication going on to make this system work. The operator panel has to communicate with the main computer. The main computer has to... Ruby, you're too cute. You're too cute. Bork! The operator panel has to communicate with the main computer has to communicate with the Raspberry Pi on the vehicle, and then the Raspberry Pi has to communicate with the motor drivers. But what happens if a chain in that communication breaks? It could be really dangerous. The operator or the control system could end up in a situation where it loses control of the motors. So every single communication pathway between all of these devices are monitored and have a plan to safely shut the ride down if they fail. Between the operator panel and the main computer is a WebSocket. The WebSocket passes data between the operator panel and the main computer. This allows the operator to control the ride and view its status. It's easy to tell when a WebSocket breaks based on the way it's designed. So when a WebSocket breaks, the main computer detects that and sends an e-stop message to the main ride vehicle to shut down the ride. The computer on the ride vehicle is constantly listening for messages from the main controller. If it doesn't receive a message every single second, it will assume that the main controller has failed and the vehicle will come to a complete stop. The same standard goes for the motor drivers. The motor drivers are constantly listening for CAN messages from the Raspberry Pi every single second. If it doesn't receive a message within a second, it will assume that something has gone wrong with the main computer on the vehicle and it will shut down the motor. It will also send an e-stop message back to the main controller in hopes that it will shut down the other motor. And then it's the same thing the other way around as well. If the main computer doesn't receive any status messages over CAN from the motor driver, then it will assume something's gone wrong, and it will send an e-stop out to the other motor to shut it down. The vehicle here is constantly tracking its location using all these ArUco markers on the floor and this camera down here. Each one of these ArUco markers has a unique geometry, so the computer can tell exactly which one it's looking at any given time. And because I've told the computer where every single one of these ArUco markers is relative to each other, the vehicle can figure out where it is based on which ArUco markers it's seeing. It is also constantly receiving messages from the main controller about where it should be based on the ride profile. I made this ride profile in Blender, and I used Python to export it to a CSV. The main controller opens up that CSV and sends the data to the ride vehicle as the profile progresses. If the vehicle is ever too far away from where it should be, it'll trigger an e-stop. This means that either a motor broke or something's wrong with the profile, but for whatever reason, the vehicle isn't able to keep up with where the computer is telling it to be. When this happens, an e-stop is triggered and the ride comes to a complete stop. The operator controls the ride through this. This is a software interface I've been developing to run on my tablet. It has control buttons across the top here and a position map down below. The position map is super helpful for troubleshooting and debugging, but it's not what we're here for right now. Right now, we're going to talk about how these controls make the ride safer. Now, there's a golden rule in safety-related control systems. You always want the ride to be very easy to stop, but much harder to start back up. A ride that is at a complete standstill is safer than a ride that is moving, so you want to make it easier to make it safe and harder to make it unsafe. And that's exactly what I've done with this controller. I made the e-stop button here very large and bright red. As soon as you press it, the ride comes to a complete stop. Additionally, the rider also has an e-stop button on the vehicle. As soon as they press this button, the same thing happens and the ride comes to a complete stop. Starting the ride back up again requires more safety so it doesn't happen accidentally. The first line of defense is actually just making the start button smaller. That way it's harder to press accidentally. So when you press the start button, just like this, a pop-up opens up asking you to confirm that you meant to press that button. The ride will not start moving until the operator presses that start button and then presses the confirm button like this. This means that there's no way to accidentally press a button and get the ride to start moving unexpectedly. I'm sure we've all accidentally pressed buttons on our phone and crazy things start happening. A system like this prevents an accident like that from causing unexpected motion and hurting someone. There's one more safety feature in the operator control panel that I want to talk about. I've added a manual drive mode that allows the operator to drive the vehicle around using this joystick. But you see, I can't actually move the joystick around right now. That's because I've required two-hand operation. The operator must first hold down this joystick enable button with one hand, and then they're able to move the joystick around with the other. If either hand lets go, the joystick returns to that center position and the vehicle stops moving. Requiring both hands to drive the vehicle around ensures that the operator doesn't get distracted while driving doing something else with their free hand. Stop the ride even in the biggest emergencies. The rider can reach down and switch this main disconnect switch from the seat. This main disconnect switch disables all power to the vehicle. That means no power to the motors, no power to the motor drivers, no power to the main controller, and it even cuts the laser gun. With this, even if everything else goes completely wrong, the rider can stop the ride and stay safe. So now we've learned about how the mechanical design of this ride, the communication monitoring, the e-stops, and even a main disconnect keep the rider safe while riding this ride. Thank you for watching this video about the safety of my ride system. Be sure to subscribe to see any future progress on this ride. Next up, we're building animatronics.